All right, so the next task for us is to create the Dijkstra's pathfinding algorithm based on this algorithm that we found on Wikipedia. So this is a well-known algorithm, and there are good books such as the CLR algorithms book that lists this and many other good algorithms. We're going to use this as a base. So the first thing, let's look at the kind of data structures that we're going to need for it. We are going to have a queue, apparently, and the queue is going to hold vertices that we need to visit, starting from the source vertex, right? And we're going to go through these vertices and try to build that shortest path. Okay. We're also going to need somewhere to store distances. These distances are going to go from the vertex, from each vertex, to the source. So basically the shortest path so far to this vertex that we have found. That's what we're going to store here. And the previous is going to be a data structure that holds links to the previous node that we have explored so far, so that we can rebuild the path once we find the destination node. Okay. We had a similar data structure called parents when we were building the depth first search algorithm for pathfinding, right? So now we're going to stick to whatever this algorithm is calling these things. So let's do it. So let me start this function. I'm going to call it Dijkstra. It's going to have a source and it's going to have a destination, all right? So in the meantime, we will also have a value for the queue. Let me call it toVisit. Okay. And it's also going to have a value for the two maps, which is one is going to be distance. Okay, and the other is going to be previous, to hold the previous nodes. All right. So we have the names of the variables. Let's figure out the types now. So toVisit is going to be the queue. So I'm going to create it as a mutable queue. Right. Okay. And let me assign to it an empty queue to begin with. Okay. So now the distance is going to be a map. So it's going to be a mutable map so that we can actually update its values as we are finding shorter paths for particular vertices. Okay, and when we decide about the map, we need to specify the types. So this map is going to go from the vertex to the value, and the value is the weight, and the weight has the type of double. Okay. So that looks good to me. And let's initialize it to an empty map. Okay. And guess what? This queue also needs a type parameter. We are going to store vertices in this queue, so that's one thing I forgot to mention. All right. So for the previous value, it's also going to be a mutable queue map. Except it's going to go from vertex to vertex, because it's going to tell us which vertex is before this vertex in the path that we have found so far. Okay, so we should be good to go with the data structures now. We could actually implement the algorithm now, I think, right? Now, this function returns a list, and list is going to be a path that we have found, a shortest path. So for this, we also need a path. So I think we can kind of steal it from. Why not we write it out from scratch? So the path is going to be a variable path of type list, and that list is actually going to have vertices, and let's initialize it to an empty list. Okay, and then if we find no path, then we can return the same path, the empty path that we have created. Okay, So let's see, what's the next thing? The next thing is to look at the algorithm and to see what is it that we could add from here. Okay. The first thing to do is to initialize these data structures. All the distances should be initialized to infinity because initially we don't know a good route to any of the nodes, any of the vertices, right? So let's do that, okay? For that, we're gonna need a loop for v gets one of the vertex, and for each vertex, in other words, what do? We assign a distance to that vertex to be infinity, okay? So we have distances, so this map gets a new member, and that member should be from vertex v, and that vertex should point to infinity. How do you specify infinity in programming? Turns out in Scala, for doubles, there might be several ways how to do it. Okay, so we could just enter a huge number, something like 99999, and then hope that no path will be longer than this 99999, which is not foolproof, because what if the path actually is longer? Then our algorithm is going to break. So this is not good enough. We may have to look for a maximum value of doubles, and turns out, yes, we could find it. We could define it like this, which is pretty good, but there's even a better way. So it turns out in Scala, for doubles, we can ask for positive infinity, which is the maximum positive number, or actually beyond that. Nothing is going to be greater than this positive infinity, which is exactly what we need for this algorithm. Okay, so good. Now, the other thing is to initialize previous to undefined, but if we don't add anything to the map previous, then it stays undefined for these keys that have not been added, right? So there's really nothing for us to do for that particular line of the algorithm. And then finally, it adds all the vertices to the queue, which is one way how we could do it. So I guess we could enqueue all the vertices here. So let me do it for the sake of to visit. It doesn't seem to be the most efficient way to do it, but according to that particular algorithm, we could do it this way, right? Another option might be to add those vertices only as we encounter them. Because if we have not encountered them, then maybe there is no point of even bothering about them, right? What if there is the whole chunk of the graph that's not even connected to us, right? It would be kind of silly to go through those vertices even now, knowing that we will never reach them anyway, right? So that might be another option, to enqueue the vertices as we go through them. Okay, so maybe we could start it like that. We could enqueue by enqueuing the source, enqueuing the very first vertex. All right, and then what we can do, we can go through all while the queue is not empty. So while to visit non-empty, what do? We get the new vertex u from queue with the minimum distance u. Okay, so we need to find from all the vertices in that queue the vertex that has the minimum distance. So in fact, this looks more like a priority queue to me. And priority queue might provide us automatically if we were to store the nodes and the weights to those nodes in that queue. Since that's not quite how we have set it up in our algorithm, I think I'm going to change it somewhat. I'm going to change the toVisit data structure from queue to a, we could have it as a list, or we could have it as a map that actually, we need a mutable data structure so that we can take things out of it, right? Okay. All right. So I think one way to go forward would be to use a different data structure for toVisit. So instead of having a queue, because we are not really going to use the properties of the queue, the FIFO properties here, we can use a set. Okay. And the reason behind my thinking is that what we really need here is we need to add members to toVisit set. We need to check the whether they are still there, and we may need to remove from toVisit, and that's all we need to do. And for that kind of operations, the best data structure, I believe, is a set in many cases. Okay. All right, so let's change it to set then. toVisit is not going to be a queue; it's going to be a mutable set. And of course, we need to initialize to set. And while we are here, I notice there's another problem here. So it returns a list. So this list needs a type. This list needs a type of vertices. That's the list, the path that we are going to return. It will contain vertices. So that's what we had to add. Otherwise, we would have an error message here. We would find it anyway. Okay, so now that we have toVisit is a mutable set, and queue does not work anymore, but we could do something like this. We could add the source to that set, right? And then we can check toVisit non-empty. So non-empty set also apparently has that property, so that's very nice. What do we do? So while it is not empty, we get a vertex with the minimum distance of u, which means we're gonna have to go through all the elements of the set. Okay, so we are going to have to for let's say vertex v gets from the set, and except we need this, all right, something like that. And we're gonna have to search from the minimum element, right? So in the minimum element, we need to specify it. So let me create a comment here, right? So find the vertex with the min path so far, okay? With the minimum length of path so far. So for that, we're gonna need to have a min path or min value. Min value. Let's say min value. Let's keep it that way, or min weight. And the type of this is once again gonna be double. And let's initialize it to and here once again we can have positive infinity or the max value up to us. Okay. So now we have min value, and we need to, as we go through each element of the set, except can we do it like this for the sets? Cannot resolve the symbol for each. So we want to go through the set, except that set has a name, of course, right? So the set has a name toVisit. That's our set that we want to visit. And then for each element here, we need to get the weight value. Let's say weight is equal, how do we get it? We get the weight, we get the actual distance till that vertex. Okay, so we look up the distance to that vertex. Okay, and now we can compare whether that distance is less than the minimal distance, right? So that's a simple way how to find a minimum value. If min value is greater than the weight, then we are going to replace min value with the weight, and we also need to keep track of the mean vertex. Let me call it u perhaps, and then we're gonna have value u, or variable because it can change, and this also can change. Actually, this may not. All right, so this is going to be the minimum vertex, and we start out, let's say we can start out with the destination, right? It's of type V, and let's start out with the destination. Okay, because we are still going to replace it soon enough. We could even start with the source, I don't care. As soon as we find that the min value is greater than W, that we have found the lower min value. So therefore, if it's the case, then we also need to replace U with V, and we have found the minimum U, the vertex with the minimum destination. So what happens here is we are looking for the vertex in Q with the minimum destination to the U, with the minimum distance to that. Okay, so all this one line converts to this whole loop, or rather these lines of code in my code. Okay, that's why pseudocode is actually nice, where you can use more or less human language to describe the algorithm so that we can understand it, in short, the essence of it. And then we actually need to program, then we need to figure out how do we encode it, what data structures to actually use it for it. And that's what we've been doing here today. All right, so we have found the smallest one. As we have found it, we need to remove it from our set. And then we are going to use the same vertex further on, later on in the algorithm. So after this for loop, we have found the smallest, so we need to remove it from the toVisit. So toVisit dot remove, not reduce, remove U. Okay, and for us to be able to do that, actually we need to wait a minute. What I have done here, I need to move this out, right? Because this is where we define min value. We also should define the min vertex U, the vertex with the shortest path so far. And this is where we remove that vertex. And now we can actually use that vertex and visit all its neighbors, right? So according to this line, for each neighbor V of the vertex U, such that V is still in the queue, right? So therefore, we're going to do it like this. For how do we know who is the neighbor of U? We need to look into edges. So for V gets edges of the key is v, so u. And in fact, what we're going to get here, we are going to get an edge e. And that edge, remember, that edge has both the weight and the vertex that it points to. Okay, so for each of those vertices, what do? First, we get the v is equal e dot target. That's our value, let's say. All right, and the value weight is going to get e dot weight. Okay, and in fact, this particular one we could probably just use in the code directly down below that we're going to create, right? So we'll see. So now we have the target. What we need to still check whether that target is still in the set of the nodes to explore. Okay, so therefore, if to visit dot contains, and we're looking for v. If it still is in there, then we do what's said here. We need to calculate the alternative distance alt by using distance to u and also distance between the edges, between the vertices u and v, right? So we're going to create a value alt of the type double, and we are going to assign it distance to u, okay? So we're looking up the distance from the map of distances to the node u, to the vertex u, and we need to add to it the edge value, the weight of the edge between u and v. And that between u and v we got here in the w. Okay, so we could, in other words, just use this directly to be more explicit this way, so that the code would also be more readable here. Okay, and we have found the alternative value, we have calculated it, and now we need to check whether the alternative value is shorter than the current distance to the v. Okay, so in other words, if alt is less than the current distance to the vertex v, this to the v, see, it's very convenient to actually use those maps here. All we need to specify is the vertex, and we can get the distance to that vertex. So let's say, what do we do if that is really the case? Then we have found a better route. So therefore, we need to update the distance to v to the alt and the previous to v to the u. Okay, so then this to v gets alt, so it gets the alternative distance, the shorter one, and the previous, the link to the previous node to v is going to be u. Okay, so this seems about right to me. At least this seems to be very close to this algorithm. We haven't seen yet whether that algorithm is performing as advertised, so that we need to test. Okay, but before that, let me try to compile it, and it seems like there are no compilation errors. Okay, so if the algorithm works as advertised, then the map to the previous values is going to have a nice path to to our source. Okay? So therefore, as soon as we find our destination, we could try to figure out that map. I don't think that's quite correct, because what if we find the shortest path to the destination after we have encountered it the first time already, right? What if we have found some very long distance around roundabout to the destination, but we are still yet to find a much shorter distance to that one? Similar to our path to the LA from Riga, if you remember in that picture, where the shortest path was not through New York directly to LA or through DC to LA, but rather from Riga to DC, then to New York, and then to LA, or something like that, right? So I guess we need to go through that algorithm all the way through until there are no more nodes to explore, and only when we are done with the algorithm, with this while loop, okay? So only then we can actually calculate the path, okay? So we are done with Dijkstra's algorithm. We need to reconstruct the path. Okay, but before we move on to the path, I think I remember one thing that we haven't taken care of. Okay, so if you remember, the algorithm proposed that we just add all the vertices to the queue, to the set. Okay, and I said that might not be the most efficient way to do it. We might add the vertices to the set by starting from the source, and as we encounter new vertices, then we could add them to the set if they haven't been visited. So, and that could be adding it here. But right now, just to go along with the algorithm, with the simplicity, I think we could do it here exactly as the algorithm says, even though that might not be the most efficient way. But at least we're not going to add complexity for us, for our thinking here, on top of this algorithm before we actually know that this algorithm works. Okay, so I just added this line. In other words, I added all the nodes from the vertices to the list of to visit when we start. Okay, and then we're going to go through this list. We find the shortest one, which initially should actually be the source node. So we haven't done this. Distance to the source needs to be set to 0. So let's do that. Distance to the source is equal to 0. Okay, so that we can actually find it as the shortest one, and then we can build from there in that algorithm. Build the path. So I think we are fine with it now. Let me just recompile it once again. No more errors, okay? And now let's reconstruct the path. And we can reconstruct the path from the previous list. And that is going to be similar to what we've done before, I believe, okay? So let's start, let's say we have a value of VP. So that is going to be our vertex node. Let that one start with the destination. Okay? All right. And now we're going to have a loop. Let's add it to the path as well. Okay, so path is equal DST. Okay, so we're adding DST to the path. And now let's check while VP is not equal to the source, So while we have not reached to the source, what we do is we will look for the next link using the previous. Okay, so VP is equal previous from VP, and let's add VP to the path. See? So what's happening here is we start out with the destination, with the end of the road, and then we're gonna loop through this. We're gonna climb back to the previous node, and we will build the path that way. And what we know is that this previous map has been built in such a way, thanks to Dijkstra's algorithm, that it will always point to the node that leads to the shortest path. Okay. And now let me compile it once again. I think that we might actually be good, but we're not. So reassignment to value. Aha, so of course this needs to be a variable if we want to reassign to it. Okay, let me compile once again. So it does pay to compile once in a while while writing the code. And now we should be able to actually test it. Okay, so we have the test program here, and finally we can add, let me comment this guy out, g.dijkstra, and what I want to look for is I want to look for the path from Riga to LA, at least initially, right? Because that path was kind of tricky one. So that path was not necessarily the obviously shortest that's on the list. What I mean, it was not obviously the shortest that's in the picture, right? But we had to go down, up here, and here to get to the LA, the shortest possible way. Let's see if our algorithm can figure it out. All right. So let's print it. Let's print that path, and let's see how it looks like. Right. So let's run it. And it says that the shortest path from Riga to LA is Riga, DC, New York, LA. Riga, DC, New York, LA. It found it. It found it very nicely. So I would say we have reached our goal. I just want to do one more thing to make the output a bit more prettier or more informative. I want to include the actual weights of the path as we go through them. Right? So therefore, I'm going to update this path building part of the code in such a way that the path actually includes the destination as well. All right? Not the destination, but the distance to the destination. So how can we do that? So first, we need to define that the path from the Dijkstra's algorithm is going to be not just the list of vertices, but in fact the list of vertices and double. Okay? Oh, sorry. Meaning that we will create a list that has the vertices and the distance to that vertex from the source. Okay, now that we have defined it that way, we also need to be consistent and define this list the same way. Okay, and we need to include all that in the parentheses, because parentheses denote that we are going to create a tuple, basically a data structure that has both elements in it. And that's what we're going to include in the list, right? And now we are down to the place where we actually are building the list. So whenever we enter the distance, we are going to enter not just the distance, but we are going to add distance, not the destination, but also the distance to that node. And the distance sits in this guy, right? DST. It would have been nicer for me not to add DST here, but to add VP, which is the same thing because VP gets assigned DST, right? But it's nicer from the point of view because we use VP here, and then we also use VP here in a very similar command. In fact, that command is going to be exactly the same. All right. So once again, what do I do here? I create a tuple that has the vertex and also the distance to that vertex so far. And that's what I'm including into the path. Okay. And now, right here, that path is going to be printed. So let's see how it looks like. Let's run it. Let me run it. Aha. And from Riga to Riga, we have 0. From Riga to DC, the distance is 9. From Riga to New York, the distance is 10. And from Riga to LA, the distance is 16. And that looks pretty good to me. All right. So let's just have another test. Let's look to Vancouver. All right. And let me run it again. And now we see that to the Vancouver, we have even longer distance. Riga, DC, New York, LA, and VC. And the total distance is 18. Is that how we worked out? Yes, it is. So I'd say this is the way how to create pathfinding code that actually takes account the values of the edges in the graph. And I think that's a good job, and we should stop right here. Thank you.